So the imaginary unit is the square root of -1, and there's nothing special about the little lowercase I. If you want to, you can write square root of -1 every single time, but it's just a little bit faster to write a lowercase I every time we want this. An imaginary number is just a real number multiple of I. So if I say 3I, that's 3 times square root of -1, and that's an imaginary number. A complex number is a number that has a real part and an imaginary part. And so this is an example of a complex number, 3 plus 7I. And that's also in standard form. So if I tell you the standard form of a complex number, that's a real part plus an imaginary part, like x plus yi. So exercise 1 says, add the following complex numbers. If I want a plus b, I'm going to write 3 plus 7i plus 1 minus I. And then I add the real part and the imaginary part separately. So 3 plus 1 is 4. And positive 7i plus negative I is plus 6i. That makes sense? So you add the real part and imaginary part separately. Subtract the following complex numbers. If I want c minus d, then I'm going to write -2 plus 5i minus 4 plus 3i. And you've got to subtract the real part and imaginary part separately. Like -2 minus 4 is -6, and 5 minus 3 is 2i. So don't forget to distribute the minus sign to the imaginary part as well. That makes sense? Yeah. See what I mean? We've got a lot of different questions. There's like 27 exercises in this notes, but they're all very simple, I hope. Multiply the following complex numbers. If I want to multiply, what I do is I remember that the area of this rectangle is the product of the two side lengths. So if one of these side lengths is the number 3 plus 7i, and another side length is the number 1 minus I, then 3 plus 7i times 1 minus I is going to give me the area of the rectangle. Now I just need to find the area of the rectangle. And we can find the area of the rectangle by subdividing it into these 4 rectangles. And I can find the area of each one of these 4 rectangles by multiplying the side lengths. Like 1 times 3 is 3. 1 times 7i is 7i. 3 times negative I is going to become negative 3i. And then 7i times negative I is going to be negative 7i squared. And to find the total area of the rectangle, I'm going to take 3 plus 7i minus 3i minus 7i squared. Just add up those 4 smaller rectangles to get the area of the big rectangle, and that's going to be 3 plus 4i plus 7. And who can tell me, why is negative 7i squared the same thing as plus 7? Yeah. We defined I as the square root of -1, and that means that I squared would be -1. That's what's going on there. And then finally combining the real parts, I get 3 plus 7 is 10. Voila. So this is how I multiply complex numbers. Okay. This definition says, for a given complex number in standard form, the complex conjugate is given by this little overbar. The overbar means conjugate, and the only difference is the plus or minus sign changes on only the imaginary part. So if your original complex number is 2 plus 3i, the conjugate would be 2 minus 3i. And we call them conjugate pairs because if you had 2 minus 3i, the conjugate would be 2 plus 3i. It's a one-to-one relation. It goes both ways. Exercise 4 says divide the following complex numbers. So if I wanted to divide a divided by b, this is going to be 3 plus 7i divided by 1 minus I. And the only way to do this in standard form is to say a divided by b is the same thing as a times b conjugate divided by b times b conjugate. And it's okay to multiply the top and bottom of a fraction by the same number because it's like multiplying by the number 1. It doesn't change the value of anything. So what is the conjugate of b? What's b conjugate? 1 plus I. So the plus or minus sign changes on just the imaginary part, and I get 1 plus I. And that means I have to multiply 2 times. I have to multiply in the numerator, and I have to multiply in the denominator. So in the numerator, did we already do that problem? Let me see, what did we just multiply? We just multiplied 3 plus 7i times 1 minus I. So we haven't done this problem yet, because this is different. This is 1 plus I. So let's do the numerator first. Three plus 7i times 1 plus I. It's going to be 3, 7i, 3i, and plus 7i squared. And altogether, the numerator is going to be 3 minus 7 plus 10i. And then for the denominator, I get 1 minus I times 1 plus I, which is 1, negative I, positive I, negative I squared. So it's 1 plus 1 is 2. I'll give you a minute to catch up writing if you need to. So we got two multiplication problems. We multiply across the top of the numerator, a times conjugate of b, since that's an orange. 7i squared is negative 7. And then we also multiply b times conjugate of b in the denominator, 1 minus I times 1 plus I. That's here in green. Negative I squared is the same thing as plus 1. That's where I get 1 plus 1 is 2. And notice the off-diagonal squares, this plus I and negative I, those cancel each other out. One of them's positive, one of them's negative. And that's not just a coincidence to this problem, but that's actually by design. The reason we divide complex numbers this way, the reason that we choose to multiply the top and bottom by the conjugate of the denominator is because whenever I multiply a complex number times its conjugate, I'm going to get opposite plus or minus signs on these boxes in the off diagonal, and they're going to cancel each other out. Well, on the main diagonal, I've got a real number and then another real number, because I always end up with I squared. And when I add two real numbers together, I always get a real number. And we like having a real number in the denominator because it's easy to divide the real part and easy to divide the imaginary part separately. We know how to divide real numbers, and we can simplify back to a standard form. So that's intentional. That's the reason why we do it that way. Sometimes people think this is handy. It's a little shortcut. In the numerator, you still have to multiply. But in the denominator, whenever you have b times b conjugate, suppose b is some real part plus an imaginary part, then b conjugate would be x minus yi. This is always going to give me x plus yi, x minus yi. So I've got x squared negative y squared I squared plus xyi minus xyi. So, like we said, these always cancel. And what I'm left with is always x squared plus y squared. Because I squared is always negative 1, so two negatives make a positive. And where it says RE of b, that means the real part. And likewise, IM of b means the imaginary part of b. So rather than having to draw a square and multiply in the denominator, if you just square the real part, square the imaginary part, add them together, that can be a little shortcut. Do a little example of a shortcut problem. If I had 1 divided by 3 plus 4i, in the numerator, I have to multiply by the numerator times 3 minus 4i. This is too loud. And I didn't notice how loud it was until it cut off. I still have to multiply by 3 minus 4i. So 1 times 3 minus 4i looks like this. In the denominator, I just think real part squared plus imaginary part squared. 3 squared plus 4 squared is 5 squared, right? And so in standard form, my number would be 3/25 for the real part and negative 4/25 for the imaginary part. So a little mental math trick. Okay, so we learned how to add, subtract, multiply, and divide complex numbers. Next, we've got integer powers of I. If I ask you to simplify these, you already know I to the 1 power is just I. And Gwen said earlier, I to the 2 power would be negative 1, right? What's I to the 3 power?
Negative I.
Yeah. Right, because that's I squared times I. So it's negative 1 times I. So it's negative I. What's I to the 4th power?
What?
Yes. And you can think of it as I squared times I squared, which would be negative 1 times negative 1, which is positive 1. What is I to the 5th power?
I.
Yeah, because I can think of this as being I to the 4th power times I, which is 1 times I. What is I to the 6th power? Yes. Because that's like having I to the 4th power times I squared, which is like having 1 times negative 1, which is negative 1. What's I to the 7th power? Negative I. Because that's like having I to the 4th times I to the 3rd, which is 1 times negative I. Lastly, I to the 8th power, what would that be? Yes. It's like I to the 4th times I to the 4th, which is 1 times 1. Okay, what about I to the 0 power? What's I to the 0 power? It would be 1. Anything raised to the 0 power is 1. What about I to the negative 1 power? What do you think that's going to be? Yeah, the negative makes it like a reciprocal, so it'd be 1 divided by I. That's true. And another way I can represent the number 1 is by writing I to the 4th power. What's I to the 4th power divided by I? I to the 3rd power. And how do I simplify I to the 3rd power? Negative I. So the reciprocal of I is negative I. Or you could say I to the negative 1 power is negative I. 1 divided by I is negative I. Kind of weird. What is I to the negative 2 power?
-1.
Let's see. It'd be like 1 over I to the 2, which is like I to the 4th, divided by I to the 2, which is I squared, which is -1. Very good. I to the negative 3 power. Yeah. What about I to the negative 4 power? One. I to the negative 5 power. So this is where it starts repeating again, because I to the negative 5 is the same thing as like I to the negative 4 times I to the negative 1. That's 1 times I to the negative 1, which is just negative I. And then whenever I see I to the negative 6, I think I to the negative 4 power times I to the negative 2 power, which is 1 times I to the negative 2 power, which is -1. I to the negative 7 would be I to the negative 4 times I to the negative 3, which is 1 times I. And then I to the negative 8 power would be like 1 times, so it would be 1, right? So everything works really well as this kind of pattern. You notice the pattern? It goes in the positive direction from 0, 1, 2, 3, 4, and so on. 1I, -1, negative I, 1I, -1, negative I, 1I, -1, negative I. If you're going in the negative direction with the negative integers, it's also a pattern, and it just kind of goes in the reverse order, where you go 1, -I, -1I, 1, -I, -1I, over and over and over again. So it repeats on a 4 cycle. Every 4 integers, the cycle starts over. Knowing that, what is I raised to the power 2026?
Would it be -1?
Yeah. Very good. So the 2026 power is the same thing as I raised to the power 2024 times I raised to the 2 power. Well, 2024 is the same thing as 4 times 506. So I to the power 2024 is the same thing as I to the 4th power, all raised to the power 506 by a little property of exponents, which is 1 to the power 506, which is just 1, and I squared is -1. So the answer is -1. What about I raised to the power 2025? What's that? Yeah, it would just be I, for exactly the same reason. And then what about I raised to the power 5,999? Basically, you find the closest multiple of 4. In this case, 6,000 is a close multiple of 4. And then you think, how much do I need to add or subtract from that? And if I need to get 1 less than 6,000, I to the negative 1 power is negative I. Yeah. What about this? I raised to the power negative 2026. Let's see. It's harder for me to do the negative ones. But I'm still going to reach for the nearest power of, the nearest multiple of 4, I mean. The nearest multiple of 4 is either 2024 or 2028. Multiply times I to the 2 power, which is negative 1. Good, good. What's I to the negative 2025?
Would it be I?
It's going to be negative I.
No, I did that wrong.
And you know, there's more than one way to think about these. Another way I could think about exactly the same question is I could say, well, what about I to the negative 2024? And then I would have to go multiply by I to the negative 1. I to the negative 1, however, is also negative I. So you should get the same answer even working it different ways. Okay, this last one now is I raised to the power negative 5,999. That's going to be what? Yes, that'll be I. Very good. All right, so we got our multiples of I out of the way. Let's talk about the complex plane. The complex plane is a way to visually represent the complex numbers. The horizontal axis is the real number line. So if a point falls on that horizontal axis, it's a real number. The vertical axis is the imaginary number line. So if a number falls on exactly the imaginary axis, you've got just a strictly imaginary number. Notice the only point in common between the real numbers and the imaginary numbers is 0. So the point where these axes intersect each other is 0. Every other point in the plane is a complex number that has a real part plus an imaginary part. And there's a really nice one-to-one relation between points on the plane and complex numbers. Like if I point to a spot on the plane, you can tell me what the corresponding complex number is by looking at the coordinates. And if I tell you a complex number, you can plot a point on the plane by, again, just locating coordinates. So in exercise 6, it says, in the complex plane, draw points marking the locations of numbers 4 minus 2i. Boom. There's 4 minus 2i. The next one is negative 3 minus 3i. And then we have 2 plus I. And negative 5 plus 2i. Does everybody see how to do that? Cool. Like I said, a ton of exercises today. They're all very straightforward, I think. Okay, for a complex number, the absolute value represents the distance in the complex plane from 0 to z. So in exercise 7, find the absolute value of each of the following complex numbers. And to do this, I'm going to draw a little picture for you. Here's my imaginary axis. Here's my real axis. And the first number I'm looking at is 3 plus 4i. So I need 1, 2, 3. 1, 2, 3, 4. That's the point. What is the distance in the plane from 0 to 3 plus 4i? Remember, the point where the axes intersect, that's 0. So how far is it from 0 to 3 plus 4i?
5 units.
How did you know that?
Pythagorean theorem.
The Pythagorean theorem. So you're absolutely right. I've got a little right triangle here. And the horizontal side of this triangle has length 3. The vertical side of this triangle has length 4. So if I want the hypotenuse, which is the shortest distance from the origin to my number, I have to take 3 squared plus 4 squared. That's 9 plus 16. That's 25. I take the square root of 25, and that gives me the absolute value here. So I could say that for z equals x plus yi, so the real part is x and the imaginary part is y, the absolute value of z is the square root of x squared plus y squared. And that means for this number, this is absolute value 5. And for this number over here, 5 minus 12i, what's the absolute value of this number?
Would be 13.
13. 25 plus 144 is 169. That's 13 squared. Very good. Does that make sense? Okay. So the absolute value is the distance from the origin in the complex plane. Another thing that I'm going to point out before we move on is even if you have a real number, like the number negative 3, that's still the definition of absolute value, isn't it? Because in the complex plane, negative 3 is 3 units away from 0. That's how absolute value works. A vector is a directed line segment, usually represented by an arrow. And for a vector, both the size and direction of the vector are important to us. So in exercise 8, it says represent the complex numbers blah, blah, blah using vectors. let's do this. 4 minus 2i would be this point in the plane, right? But if I want to represent this as a vector, what I need to do is draw a line segment from the origin out to the point 4 minus 2i, and then make it a directed line segment. Here's negative 3 minus 3i. I'm going to put a dot there to begin with, and then I'm going to draw the vector. Two plus I is here. This is just another way of representing complex numbers, another one-to-one kind of correspondence between vectors in the plane and complex numbers. Does that make sense? Okay. Then, once we can represent these as vectors, there's a geometric way to represent sums and differences. If I want to add the number 2i plus negative 5 plus 2i, well, here's 2 plus I as a vector in red, and here is negative 5 plus 2i as a vector in green. But I just took the negative 5 plus 2i vector, which normally would go from here to here, and I just line it up tip to tail with the first vector. And then to read the result of this sum, I just look at the coordinates of where we end up. So negative 5 plus 2i is here. Take that vector, slide it over so it lines up tip to tail with the vector 2 plus I. And then you get this point that has coordinates negative 3 plus 3i. So it feels kind of nice and logical, even with geometry in the plane, to add and subtract, or add complex numbers. Now we're going to subtract them. The difference now between adding negative 5 plus 2i, which would be this vector, and subtracting negative 5 plus 2i is that when I subtract it, I'm going to keep the length of the vector the same, but when I subtract it, I'm going to make it point in exactly the opposite direction. So subtracting means you go in the opposite, 180 degree flip. And so this time, the result is what I get if I line up these vectors tip to tail with each other, and that's going to be 7 It's supposed to be 7. It's a little bit off. It's supposed to be 7 in the real direction, and then, of course, negative 1 in the imaginary direction. If you have a conjugate pair, which means you've got two complex numbers and the only difference between them is the plus or minus sign on the imaginary part, that means when you draw them as vectors, they're going to be a reflection of the other across the real axis, right? Because the real part is the same, the imaginary part has opposite plus or minus sign, and so they look like a reflection of one another across the real axis. Okay, next thing, what happens every time we multiply a number by I? What if I start off with the number 4? If I have the number 4 and I multiply by I, I'm going to get 4i, right? So let me draw the number 4i. What happens if I multiply by I again? What's 4i times I? Negative 4. So let me draw the number negative 4. What if I multiply that by an I? Then I would get negative 4i, which would be down here. And what if I multiply that by I? Four. So when the question asks, what happens each time we multiply a number by I? Every time I multiply by I, we get a 90-degree rotation. Or in radians, we could say we get, in radians, a pi over 2 rotation. Either way is correct. And I'm not going to make you do all of the gruesome math, multiplying complex numbers in standard form. But if I had this number b, where b is 3 times the square root of 2 plus 3 times square root of 2i, that would be a number, I actually don't actually know what 3 times square root of 2 is. I know it would be 6 units away from the origin, like the absolute value of 6. But the x-coordinate of this number would be like 4.24. And the y-coordinate would be 4.24. So it'd be sitting right here. And like I said, actually, never mind, multiplying this by I is not going to be that difficult. We can do that pretty easily, in fact. When I multiply by I, 3 square root 2i becomes 3 square root 2i squared, which is negative 3 square root of 2. And when I multiply 3 square root of 2 by I, this is what I get. Multiply by I once again, and I'm going to get negative 3 square root of 2 minus 3 square root of 2i. So I end up over here. And then multiply by I once again, and I will get 3 square root of 2 minus 3 square root of 2i. I'll end up over here. And then multiply by I again, and I get 3 square root of 2 plus 3 square root of 2i. So every time I multiply even the blue number by I, I'm ending up with a 90-degree rotation. This is the only bit of calculus we're going to do today. And I think this is really neat. This is maybe even my favorite part of all of mathematics. I think this is so cool, personally. This is Euler's formula. And it relates Euler's number E, which is like 2.71828, whatever, irrational number E, raised to the power I, which is square root of negative 1, times theta. And this is valid if theta is any complex number, but really what we care about today is letting theta be any real number. So pretend theta is a real number. This is equal to, in every way, the cosine of theta plus I, that's square root of -1, times sine of theta. This is an extremely important identity. And like I said, the proof is going to involve just a little bit of calculus. So how do we prove this? How would you convince somebody that this must be true? Is you say, define a complex number z such that z is going to be equal to cosine of theta plus I times sine of theta for some real number theta. So that double struck R symbol means it has to be a real number, or it means the set of real numbers. The little symbol next to it that looks like a lazy E, that means belongs to. That's just a math notation symbol that says theta belongs to the set of real numbers. So now we take the derivative. We're going to take the derivative of z with respect to theta. What's the derivative of z with respect to theta? Well, first we can take these terms separately. So what's the derivative of cosine?
Negative sine.
Negative sine of theta. And what's the derivative of sine? Cosine. Derivative of sine is cosine, and I is just a constant. And when I take derivatives, constants just come along for the right. That's derivative homogeneity. So took the derivative of cosine, took the derivative of sine. The next thing we're going to observe here is that negative sine is the same thing as I squared times sine, because I squared is -1. Now tell me if you follow this next part. Imagine I switch the order of those terms, so I have I cosine theta plus I squared sine theta. Factor out one of the i's, you'd have I times cosine theta plus I sine theta. But what's the definition of z? By definition, z is cosine theta plus I sine theta. So IZ would be I cosine theta plus I squared sine theta. It's pretty good. What we need to do next is we need to take an antiderivative of both sides with respect to theta. No, almost there. It'll be there in the next step. Let's see. Divide both sides by z. There we go. And now that we've divided both sides by z, now we can take an antiderivative of both sides with respect to theta. So we're doing the same thing to both sides. Everything's staying nice and balanced. I want to think about the right side first. Remember, I is a constant. So if I take the antiderivative of a constant with respect to the variable theta, what is that antiderivative?
Can you repeat the question?
If I take the antiderivative of I with respect to theta, what's that going to end up being?
Oh, wouldn't that just be Z?
No, but I'll show you and then you'll understand after I show you. The antiderivative is I times theta plus a constant, because if I take a derivative of this with respect to theta, right, the derivative with respect to theta of I theta would just be I. And the derivative of a constant is 0, so it would go away. So in blue, that's the antiderivative of I with respect to theta, because you can check it by taking the derivative. Still good? All right. On the left side, we're going to do something fancy. On the left side, I'm going to cancel out the d thetas that appear, because one of them is in the numerator and one of them is in the denominator. Remember, in Leibniz notation, the little d theta is talking about a small change in the variable theta. So let's say that this d theta talks about the same small change. Well, multiplying and dividing by the same small change is going to cancel out. So now, as it appears, we're taking the antiderivative of the function 1 divided by z with respect to z now, instead of with respect to theta. And what's the antiderivative of 1 over z with respect to z? I know it's been like 4 or 5 weeks since you knew this, right?
Natural log of z.
Yeah, there we go. The antiderivative of 1 over z with respect to z would be the natural log of z plus a constant, right? And we're going to name that constant c2 just because it could be distinct from the constant c1, but we'll do a little trick that's hardly a trick, but just define c equals c2 minus c1, and we'll get natural log of z is equal to I theta plus c. And then that means I can move on with just one arbitrary constant instead of 2, which is nice. Okay, how do I get rid of the natural log? If I want to solve for z, how would I get rid of this natural log? Yeah, I should compose with e. And so I can say e raised to the power natural log of z would be equal to, on the right side, e raised to the power I theta plus c. On the left side, composing these two functions, they're going to cancel each other out because they are inverse functions. And on the right side, this is the same thing as e to the power c times e to the power I theta. because that's a property of exponents. If I'm adding up an exponent, I can just separate them. Well, remember, C1 and C2 could be any old constant because they were just coming up from the antiderivative. If I take a derivative of a constant, it goes back to 0. So C1 can be whatever we want. C2 can be whatever we want. That means if I'm taking their difference, it can be any real number that I want. E is just a number, just 2.71828, blah, blah, blah. E raised to any real number is just any positive real number. So maybe I could choose to represent it like this, as long as we remember that C has to be positive. But it could be any positive number. And this is doing pretty good, I think, right now. What we're going to do is we're going to take this expression for Z that we found. Z is equal to C e to the I theta. And we are going to say, okay, Z is C times e to the I theta. We're going to scroll back up and we're going to remember, how did we define Z to begin with? What was the original definition of Z? Originally, we said we're going to define a complex number Z such that Z is equal to cosine theta plus I sine theta. So Z is cosine theta plus I sine theta. I'm going to take that definition, the one that we started with, and all you really need to figure out is, what is that constant C? And I know that this has to work for all real numbers theta. So let's choose one of those real numbers and see what happens. If I set theta equal to 0, I get the equation C times e to the power I0 is equal to cosine of 0 plus I sine 0. What is e to the power 0? 1. What is cosine of 0? 1. And what is sine of 0? 0. So in other words, C has to be the number 1. And that means if C is the number 1, e to the power I theta has to be equal to cosine theta plus I sine theta. And that's it. That's what we were trying to prove. This is called Euler's formula. E to the I theta equals cosine theta plus I sine theta. I think that's very cool. And as far as proofs go, this is not a bad one. I mean, it's got some steps to it. Each step is pretty simple. You know? I think that's neat. All right, we got like 14 minutes left. Let's see how much we can get done. For any theta in the real numbers, the absolute value of e to the I theta is always 1. So remember, absolute value is the distance in the plane, so that means the distance from 0 to e to the I theta is always 1, and that means it's the unit circle. The set of numbers e to the I theta, where theta can be anything, that would be the unit circle in the complex plane. And theta is going to be the angle that the vector e to the I theta makes counterclockwise from the positive x-axis. So the proof here is just remember Euler's theorem. We want to show that e to the I theta, absolute value, is equal to 1. So we want to show that the absolute value of cosine theta plus I sine theta is equal to 1. Well, do you remember our absolute value formula? Our absolute value formula says take the square root of the real part squared plus the imaginary part squared. Square both sides. And we get this. This is a trig identity. And this is a pretty easy trig identity to solve or to prove using the Pythagorean theorem, right? Like, here's a triangle with angle theta. If the hypotenuse is 1, then the adjacent side would have length cosine theta, the opposite side would have length sine theta, and then use the Pythagorean theorem. And that's super easy to prove this. So we know that cosine squared theta plus sine squared theta is equal to 1 because of the Pythagorean theorem. Take the square root of both sides. Notice that this is the same thing as the absolute value of this complex number. And notice using Euler's formula that that's the absolute value of e to the I theta. So this is how you prove it. E to the I theta is a complex number that lies on the unit circle in the complex plane. So if I have a complex number that's r e to the I theta, and r is some positive real number, well, the way that absolute values work, I can split this product up into separate absolute values. And since r is a positive real number, its absolute value is r, and e to the I theta has an absolute value of 1. So if you're looking at a complex number and it's represented as r times e to the I theta, that little r is its absolute value. E to the I theta doesn't do anything to mess with the absolute value. So this is called the polar form of a complex number. If you see r times e to the I theta, that's the polar form. R is the absolute value. Theta is called the argument. Of course, that's the angle that you get measured counterclockwise from the positive x-axis. And sometimes people say e to the I theta is called the complex sign, because in the real case, a sign is a plus sign or a minus sign. That puts you on the real axis. But for complex numbers, their sign could be a whole range of different things, right? It gives a direction to the number. So exercise 15 says, state the formulas for converting a complex number z equals x plus yi from standard form to polar form, where z is equal to r e to the I theta. The formulas you would use to convert from standard form to polar form would have to give you r as a function of x and y. But remember, r is the absolute value. And it would need to give you theta as a function of x and y. So that's going to be arctangent of y over x plus pi if in quadrants 2 or 3. Because we talked about that in the last lecture. How do you go from polar coordinates to rectangular coordinates? Standard form is like rectangular coordinates. Polar form is like polar coordinates. And then if you have a complex number in polar form that you want to convert to standard form, you need x as a function of r and theta, and y as a function of r and theta. These you can get quickly from using Euler's formula on that part and just keeping the r. Because remember, x is the real part, y is the imaginary part. Okay, so there's some questions about converting complex numbers from standard form to polar form, but remember you just got to use those formulas. And we did some of that last time, so I'd like to skip over that in the interest of time. If you are multiplying complex numbers that are given to you in polar form, like I want to multiply 3 e to the power I 3 pi over 4 times the number 2 e to the power I pi over 6. I would multiply 2 times 3, and then there's a certain property of exponents that tells me if I'm multiplying two exponents with the same base, I can just add the exponents. The common denominator between 4 and 6 would be 12. So what does that make? 5/12? No, 11/12. 11/12. You guys got to correct me. Yeah. Again, in the interest of time, I'm going to skip the exercise 20 where you're plotting, but think about this for a moment. What I did is I multiplied their absolute values to get the new absolute value, and then I added the arguments together. So the thing is going to get, the vector is going to get, the new vector length by multiplying the old vector lengths. But what happens to the direction of the vector? I'm going to add the two arguments together. So multiplying one complex number by another is going to rotate it by however much angle you had, in the second complex number. So it's kind of a rotation that depends on the location of the numbers. Likewise, if I want to divide the numbers 3 e to the power I times 3 pi over 4 divided by 2 e to the power I pi over 6, then I'm going to divide 3 divided by 2 to get my new absolute value. And then there's a property of exponents that says if I'm going to divide two exponents with the same base, I should subtract the exponent. So in the end, I'm going to get 3 halves e raised to the power 9/12 minus 2/12, which would be 7 pi over 12. And again, I'm going to skip the plotting part, but notice to get the new absolute value, you divide, but to get the new angle or the new argument, you subtract the arguments when you divide complex numbers in polar form. If I want to find a power of a complex number like this thing, I'm raising everything to the 5th power. Well, I can distribute that 5 into each of these factors that I'm multiplying. And then there's a property of exponents, once again, that says if I'm taking something to another power, I can multiply the powers. I can multiply the exponents. So that's like 243 times e to the power I 15 pi over 4. And 15 is 8 plus 7. So I could also write this as 243 e to the power I 7 pi over 4. Because I can subtract away 2 pi. I can subtract away a full rotation and I end up in the same spot in the complex plane. If you want to take roots of a complex number, just remember this. The cube root is the same thing as the 1/3 power. And the square root is the same thing as the 1/2 power. And the 5th root is the same thing as the 1/5 power. And then distribute that power. The cube root of 8 is 2. And I'm going to get that as my answer. Instead of 3 pi over 4, my new argument is going to be just 1 pi over 4. I still have 1 minute of class. I'm going to use it. So the last thing is called roots of unity. The roots of unity are like this. What's the square root of 1? 1. But also there's a way in which it's also kind of like negative 1, because negative 1 squared is 1, right? Kind of, sort of. So what's the cube root of 1? That's like saying the cube root of e to the power 2 pi I, which is e to the power I 2 pi over 3. And that's not the only one either. There's actually 3 roots. So positive 1 is also a root. And there's also another root, another cube root, that would be the cube root of e to the power I 4 pi, which would give me e to the power I 4 pi over 3. And if you don't see it already, the reason this works is because 1 is the same thing as e raised to the power I, and then any multiple of 2 pi, because 2 pi is a full rotation. So every time I rotate 2 pi around, I get back to the number 1. And so there are 2 square roots of the number 1, but there are 3 cube roots of the number 1. And these are called the 3 third roots of unity. Roots of unity sounds really fancy, but unity just means the number 1. So these are just the 3 cube roots of the number 1, where unity is 1. The locations of these guys on the plane are really cool. This isn't going to take me long. I'm sorry, I'm going over class. But here's the square roots of unity. Here are the cube roots of unity. Here are the 4th roots of unity. If you can't tell the little circle I've inscribed here. is the unit circle in the plane. So it's all e to the I thetas. And then the fifth roots of unity are like here. Do you kind of see what's happening? These are all evenly spaced. So here's the sixth roots of unity. They're all evenly spaced around the unit circle. And if you take any of these numbers, like here in purple, and you raise it to the sixth power, you're going to end up at the number +1. It's kind of neat.
Is there no seventh root of unity?
There are, and there would be 7 equally spaced points. If you were looking at the 500th roots of unity, there would be 500 equally spaced points around the unit circle. But that's the idea.